This tutorial is going to be a little bit advanced of my previous tutorial in which I taught you that how to estimate and plot signal to noise ratio of a single slit spectra of a galaxy or a star. So this tutorial is one step ahead, and this time I will be using a data cube of a galaxy obtained from integral field spectroscopy, not a single slit. So a data cube is basically having 3 dimensions, x, y and z. So where xy is your spectral and your z axis is the wavelength axis. So data cube you can visualize as a loaf of bread. So here each bit of slice represents lambda discrete values, and each bread position contains the xy flux map or noise map. So for your comfort, I have created this tutorial in the following steps. So step 0 will be to download our Galaxy data cube. So we will be using SDSS MANGA observations to take data cube, and then I will import required Python libraries, and then I will read and open Galaxy Fits data cube. After that I will extract flux, wavelength and error from the data cube. After that I will estimate the flux error, and then I will estimate SNR from the flux and flux error. After that I will visualize your 2D SNR map at each wavelength axis, I mean along z pixel. After that I will visualize your one-dimensional SNR plot for your each xy position of the galaxy. And finally I will save this SNR data cube as a fits image and will visualize through DS9. So these are my steps. So we'll be doing this stuff step by step. Step 0, and we will be downloading our Galaxy Fits data cube from SDSS observations, right? So I'm not going to download this data again, right? And for downloading data you can watch this tutorial given on the screen, or you can click on the top right corner of this video and you will find the video link, and I will also put the video link in the descriptions. From here you can watch this video and download the data. So our step 1 will be to import our required library. So I'll be using library Numpy, right? So this will take care of your numerical computations, number and array. Then I will import Matplotlib .pyplot as a PLT. So this will take care of your data plotting and visualization. Finally I will import Astropy. Astropy.io import fits. So this will take care of your fits file handling, reading, writing and data extraction, right? So step 1 is completed. Now what is the mistake here? Numpy, there should be Yeah, now it's fine. So now I will read and open Galaxy Fits data cube. Okay, so let me check uh, my data cube. So type here ls star fits, right? So this will extract all files having extension dot fits. So let me check. So here I have manga data cube, right? So I have around 4 data cube, log and lin. So basically log means your wavelengths are like in logarithmic space, and lin cube means your wavelength values are in linear space, right? So let me choose a lin cube, right? So this cube. So copy it and then delete this line, right? And then I will open my fits file, right? So for that, type here variable, say cube, right? And then give here a function fits dot open, and you can give here file name as a string, right? So here it is your cube, right? So basically this reads data cube, right? And then you want to know what this data cube header contains. I mean, yeah, SDU contains. So for that, here type here comment extract information, right, about data cube. So type here cube and give attribute dot info and run it. So here you can see that you have this file name, right, and you have this primary, you have serial number of the SDU, and you have name of the SDU. You have type cards which contains comments, keyword, and some other information, dimensions, x, y, and z dimensions, and format, right? So what is our interest? We have to extract our flux data, your inverse variance, right, and your wavelength, right? So your second SDU, your third, and your seventh, right? So let do the extraction one by one, right? So yeah, so first type here extract data, okay? So here you can type here data equal to just extract say flux data, right? So give your variable say flux, and then you can give here say cube, right? Cube, and then you can give your SDU name as a flux, right, in a string, and then attribute dot data, right? So if you check this flux, then this is how it looks like, okay? And you can check its shape. So flux dot shape attribute, and see it has this dimension 6732 z axis. This is your y axis, and this is your x axis, right? So in same way you can also extract the you can also extract your inverse variance, right? So for that, type here ivar equal to cube, then copy this keyword and put it here and give dot data attribute, right? So if you print here, right, and its shape is same as your flux shape, right? Now we have started the two things. Now extract wavelength. Extract lambda, right? So you can type here wavelength equal to wave, right? So just type here lambda, simple. Then give here cube and copy this keyword say wave, or you can also right now give here number 6 corresponding to your wave SDU number and dot data, right? So let's see what your lambda printing. So yeah, this is right, and see this is the difference of your each consecutive numbers. There should be double F, not single. Yeah, you can see there is one. Okay, this means that your each consecutive wavelength is linearly spaced, right? You can also check the shape of this wavelength. So it is 6732, right? This is the z-axis. Okay. Now we have extracted three stuff, three keywords: flux, inverse variance, and lambda, right? Now I will be estimating flux error, right? So flux error you can see it can be given as a 1 by inverse variance. So basically your inverse variance is 1 by sigma square, right? So you have to convert it to sigma and then take the square root, so it becomes your standard 1 sigma error or standard deviation, right? So type here variable say flux error and you can give np dot sqrt 1 divided by your inverse variance, right? Yeah, there is some error, but ignore that error because it is dividing by 0, right? So if you check here flux error, this should also be same as the shape of your inverse variance and your flux shape, right? This is how it looks like. Now I will estimate SNR of a data cube, right? So I will use this formula, flux cube divided by flux error cube, right? So type here SNR cube, right, equal to flux divided by your flux error. Okay, so if you print the SNR cube, this is how it will appear. Okay, and its shape should be same as your earlier. Okay, so this is how it will appear your SNR. So this will your SNR data cube, right, having dimension z, y and x. Okay, so your now I will visualize this SNR 2D at your each z pixel or wavelength axis. Okay, so for that type here plt dot figure, right, and give a function here, then type here plt dot plot sorry, pt.im. Okay, because we want to show the 2D image, not 1D scatter plot or something, or some 1D plot. So for that we need to give here a 2D slice of the SNR. Okay, so for that give here either cube your SNR, not here SNR, SNR cube, and then give the indexing. Okay, so give here a square bracket, and you want your flux map at each z. Okay, so give here, say I want to get flux map at say 1000. Okay, 1000 index of z. Okay, total we have z index 6732, right? And then you want to extract your all y-x pixel and your all x-axis pixel. Okay, so basically this is my, say, SNR cube, and this becomes your z, this becomes your y, right? This becomes your y, and this becomes your x. Okay, so it gives your SNR cube at x, y, and z. Okay, in this fashion. So this is like the way of indexing is really different, and it goes in opposite manner, right? So now you can see there is a plot, right? So just type here plt.show for completeness, and you can give a color map if you want. plt.colorbar, right? You can see this is the flux map at 1000 index, right? You can also give it to say index number 1. So this is how it looks like. Give it to 2. So every time the index will change. Okay, you can give to 2000. So this is how it looks like. You can give say 5000, and you can also go to the last one. Okay, 6731. So this is, there is nothing, is blank. And if you go to the higher index other than this number, then you will get some error or nothing, right? There is nothing. So index is out of bound. So we just put here say at 3000 index of wavelength, right? So this is my flux map. I can give a title here, plt.title. This is my SNR map at z equal to 3000, right? Index of lambda, right? And these are your x-axis pixel, which is 34 pixels. This is your y-axis pixel, contains 34. Here you can see that now your z-axis is like not coinciding. So here you can give origin equal to lower. So now you can see at your left bottom, your origin is at 0, 0. Earlier it was on the top and the bottom. Now they are coinciding. Okay, so this is my SNR map at single wavelength. You can change the wavelength, you get a different as SNR map, right? Now I will visualize a single spectral, okay, Multipro means suppose I want to get a spectral at say x equal to 1779 at the center. So for that I will type here plt dot figure and then type here plt dot plot and here you need to give your x-axis and y-axis. Okay, so x-axis is same, so your lambda, and then your y-axis should be your so your y-axis should be flux. Okay, so flux should be 1D. So for that type here, or in this case you have to give your SNR. So SNR cube equal to your full your z-axis and 17. Okay, so it means at central aspects, right? And type here plt dot so, right, run it. So here you can see that you have your own aspect right at your 17. You can change it, say 2017, right? So basically this becomes your one thing, your SNR cube, right? So basically your wavelength, this becomes your y and this becomes x, so it gives at x comma y. Okay, a spectra at x comma y aspects, right? So just change it, make it say at 0 spectral. So there is nothing here, only a line is there. So you can change it 20, still nothing. Stay 2015. Yeah, there is something, some lines are visible. Okay, this is how we can 24, 15. You can go to say 34. See, this is bound. Okay, so there is in Python there is 0, so it will go only up to 33 aspects, right? So this is how we can do it, right? So I can give a title here so that you can remember. And this is my SNR pixel plot at x comma y. So just make it here say 18, right? At x comma y equal to 17 and 18, right? So this is how my SNR of a single spectral will look like, right? And this is here my x-axis is the wavelength and y-axis is the flux. So let me give the plt dot x level. You can mark as a wavelength at wavelength and plt dot y level. You can mark it as a SNR, right? This is how my SNR of a single or individual spectral will look like, right? Now this much we have done. Now we can save this data cube as a fits image. Okay, in this fashion, so that you can use it using other software such as DS9, and you can visualize, right, in a single go. So for that, type here fits dot write to, and then you can give your file name. So SNR cube dot fits, right, and give it a string, right, and then you can pass here your data. So your data, right, so this is your data. So the data is here, right, SNR cube, right, so SNR cube, and then you can write here overwrite equal to true, so that if you again this code again it will overwrite your fits file. Okay, so run it. It means your SNR cube fits has been saved in a directory. So let me check. Is it there? So type here ls star fits, right. So yeah, so here you can see that, yeah, so you can see there on 26 April, and this is the time, right, and here you can see that this is my cube fits has been saved. Okay, so our next job can be like visualize this cube using DS9. Okay, so let me open DS9. So let me open DS9 here. So my DS9 interface has opened. Now I will go to their file, right, and then open, and then I will go to my directory, and I will look for the same file snrq.fits. So SNR, so here is my cube, right, upload it. So you can see, you can make it zoom version, right, so zoom fit. So here's a cube, right, and here got a dialog box. So you can see your this is my z-axis, so play it, and here you can see that its SNR map is changing. Okay, so you can give different color to visualize black body. So this is, you can visualize, right, in this fashion. So this SNR map is showing at your each z axis along lambda. So lambda 1, lambda 2, lambda 3 up to 6732 index. So this way you can visualize your data cube in your 2D map, right. So I hope this got the idea. Now let's go back to my code and review this code once again, right. So our objective was to visualize our SNR data cube of a galaxy obtained from your SDSS MANGA observation using integral field spectroscopy. So we have imported our library Numpy, Matplotlib and fits. Then I have read my fits data cube. I have extracted the information. Then I find out that there's my flux, inverse variance and wave header data unit to be extracted. So those things I have extracted individually. Then I have find out the flux error by taking a square root of the inverse variance, right, and then I have compute the flux error in form of data cube as a SNR flux divided by flux error, and then I visualize my 2D map at your each wavelength axis or your along z pixels, right? So this is one of the map along z equal to 300 index of lambda. After that, I have visualized my 1D spectra at your each xy position or spatial of the galaxy, from inner to center to outer region of the galaxy. This is how it appears. And finally, I have saved this data cube into the feed format, and then I have visualized the individual maps in a video format using DS9, right? So I hope this tutorial has helped you to gain some insight about SNR map plotting, 1D and 2D visualization, and you can reproduce using this code, and any manga data cube will work for this code. And let me know if still you are not able to produce, so you can write me in the comment box and I will be happy to help you. So thank you, and stay tuned for the next tutorials on astronomy.